Good afternoon, I am Mr. Ish. Thank you for joining me for this video where we are talking about, in a general manner, a topic on chemistry, but the viewers would consider this more organic chemistry than general chemistry. However, it's bridging both of those disciplines very well, and it should be good level here for 12th grade students. You are looking here at the word carbocation and carbanion, but if I were to just isolate this part right here and this part right here, you know what we're talking about: cations and anions. You know what they are. Cation is a ion which has a positive charge, anion is a ion which has a negative charge. The fact that I have this carb before is indicating it's based on a carbon atom. It's a carbon atom which is serving as a cation or an anion, hence the fancy term before you. But at the end of the day, it's still ions, as you would know in general chemistry. Carbocation would be anything which would look like this. You know this right here is carbon. You know in terms of its basic structure and its valence, it has a valence of four valence electrons, hence you can form 4 bonds, but a carbocation would be designated as that. A carbanion would be designated as this, where you have that. Now you see the difference between the two, but again I'm telling you, at the end of the day, it's still an ion, but it's an ion of a carbon. This is just a carbocation, and that's a carbanion. In this video, we're focusing on the behavior of this to understand how cations and anions behave. When you're looking at this structure right here, a cation, what are the items which immediately come to your mind? How about these following points? It's electron deficient. Because it has a positive charge here, it must be deficient in an electron, and that could be a good item which would come into your mind. It would be less than your ideal octet, or less than the octet. Obviously you're not going to have an octet over here. You have a deficiency here with regards to that. When you're looking at this, what are the items that are coming in your mind? It's obviously electron rich, and it obviously has 1, 2, 3, 4, 5, 6, 7, 8. It has the octet. How about I bring in 2 fancy terms to complete this little exercise for you? One would be this: it's an electrophile. And this right here would be, it's a nucleophile. This very much would be something like a Lewis acid. That very much would be something like a Lewis base. This has the ability to seek out other atoms in other compounds which have a deficiency of electron, so it can share some of that excess charge it has. This has the ability to serve as a recipient for electron rich species that it can bond with and fill its deficiency. It's an electrophile. It's looking out for electrons so it can complete that deficiency it has. The electron richness of this species makes it behave in an attacking manner. The electron deficiency over here makes it behave in a manner such that it will be the recipient of reactions. Let's consider this concept here of an inductive effect. Inductive effect is the pull of electrons by electronegative atoms. You know fluorine, oxygen, nitrogen. These are your electronegative atoms. I'm only naming these because they end up being quite electronegative in terms of how much they can induce the pull of electrons. Fluorine, oxygen, nitrogen. This type of compound, since it's electron deficient, it doesn't want to be next to electronegative atoms because it would pull away the deficiency it already has. These electronegative atoms, if they were attached to this carbocation, it would make it even more electron deficient because these atoms would pull away at that deficiency. Consider this compound over here. We don't even have to name it. We have a compound which looks like this. We have a hydrogen, we have an oxygen, and then we have a hydrogen. You see this oxygen over here? It can pull away in this direction and make this electron deficiency even more electron deficiency, and it can destabilize it. Consider this compound right here. You have an electron deficiency right here in terms of this positive charge. Now you have these fluorines attached. You have so much of a pull that it's destabilizing this already deficient area. These are not good in terms of stabilizing the positive charge, which is an area of electron deficiency. Now look at these examples I'll post. When you have here a carbanion, it wants to be next to electronegative atoms because they'll pull away at this excess negative charge it has, and it would stabilize it. Carbanion compounds which have a carbanion, you want to be seeing electronegative atoms. Let's just put here fluorine, let's put here fluorine. Again, we're not naming these, but you see those electronegative atoms, they're going to pull at this excess negative charge and it will stabilize it, and that's a good thing. How about this example right here? You have a carbanion over here and it's attached to a oxygen here, a hydroxyl group, it's a good thing. This oxygen is going to induce by means of an inductive effect and pull the negative charge towards itself because it wants to attract, because it's electronegative, it will stabilize these. When you're looking at carbocations, the presence of electronegative atoms next to that carbocation will destabilize it, and that's a bad thing. When you're looking at carbanions, the presence of electronegative atoms next to that will stabilize that excess negative charge, and that is a good thing. The opposite would be true. When you have a carbocation, then you want to have elements next to that which are electron donating. You want to see elements which are not electronegative because they can help provide some charge to that. You don't want to be seeing electronegative elements next to a positive charge. And again, here the reverse is true. When you have a carbanion or here a negative charge, you don't want to be seeing electropositive atoms like hydrogens, and you don't want to be seeing phosphorus, those type of elements which are not electronegative, because you want to be pulling this charge away towards electronegative, not adding more to it by means of electropositive elements. Keep that in mind. The last thing we'll look at here by means of the differences between two is the conjugation and the resonance effect. Anytime you have these type of species, cations and anions, for carbon compounds, conjugation and resonance is a good thing because it stabilizes it. It stabilizes either the positive charge, it stabilizes the negative charge. Consider this compound right over here. Again, we're not naming any of these compounds. We have something which looks like this. When you have a positive charge here, you can have resonance structures develop and you can stabilize that, because this deficiency can be stabilized by delocalizing it across the entire compound. Look at what I'm showing you here, resonance structures. Again, we don't have to be too fancy here, but I'm just showing you the fact that resonance structures can develop. This positive charge has now transported itself over here, and you can draw more structures. You can have this type of structure develop, which is exactly the same, except now the positive charge will have transported from here to right over here. Now your positive charge is there and you're having that, and you can develop yet another resonance structure where the positive charge will transfer itself now to right over here. You see how the positive charge has transported itself. Here's one position, here's position B, here's position C, here's position D. These are not necessarily all the resonance structures, but the more resonance structures a certain species has, the more stable it is in terms of cations or anions that it may be holding, because you're spreading that deficiency or the excess over the entire compound, and it stabilizes it. When you're looking at a carbanion over here, you could have a situation such as this. You have here, I'm just using this as an abbreviation for some compound, carbon compound, and I have this right over here. It may not truly be a carbanion, it's an oxyanion associated with oxygen, but again, it's an organic compound which has a negative charge. And you can spread this negative charge over the compound by means of a resonance structure, and you will see it to be the case right over here. I can draw some more electrons here. You see how the negative was here, now the negative is here. It has essentially transported itself over here, and then this negative charge has ended up here, and hence you're seeing the negative go from one oxygen to the other. But that right there is a resonance structure example. Let me show you just one example using the actual carbanion, and we'll end with that. You have a compound which looks just like this, and again, we're not naming it by any means. It looks like this. You can spread that negative charge over the compound by means of resonance conjugation effect. You can do it by that. You will have this negative charge come over here, and then you will have a transfer of that negative charge to the opposing side of this compound. Here's your negative charge, and there it is. You see how it was on one side, now it's ended up on the other side by means of this electron shuffling. You are delocalizing, or you are spreading this negative charge over the compound, hence you have resonance structures. Anytime you have resonance structures in terms of organic compounds, you're stabilizing that electron excess or deficiency, and it is a good thing. We'll end the video with that. Thank you for watching. Have a good day.